Hey, hi there. In today's video, we'll be discussing about a chi-square test. Okay, we'll explore different versions of chi-square test because chi-square test has got multiple applications, right? Can be used for test of variance. It can be used for to understand the test of independence, right? Whether two uh, columns or variables are dependent on each other or not, that do they share some relationship or not, for goodness of fit as well. So let's try to see what are the functions available in Python, which will allow us to use chi-square test for hypothesis testing. So I mentioned here some of the functions which we typically use, okay, in regard to chi-square test in Python. So let's take an example. For example, in an election survey, voters might be classified by gender, male or female, and shopping preference. Here we can use a chi-square test for independence to determine whether gender is related to shopping preference or not. So we have two columns. One is gender and one is whether a person likes shopping or not. So gender and shopping. So male, female, and this will be yes, no, yes, no. So both of these two columns have got two categories, right? Within itself. So let's first import all the necessary libraries. So by default, if we talk about chi-square test for independence, by default, the null hypothesis will say there is no relationship between the categorical variables, and the alternate hypothesis will say there is a relationship between the categorical variables. Let's read the data set. So you can see here gender and like shopping, male, female, and this is no, yes, no, yes, whatever it is, yes, no, and this is male, female. Now, the way chi-square test for independence work is that we have to first calculate, which is called as the contingency table. And this contingency table, as I already mentioned, is calculated using pd.crosstab. What is the contingency table? Contingency tables records the frequencies of each of the labels of the variables, right? Or each of the categories of the columns, right? So we have two columns here, and each of these two columns has got two categories each. So it will be a 2x2 matrix or pandas data frame. The cross tab will have 2x2, two rows and two columns. So if I do pandas.cross tab of gender and like shopping, we'll see it's a 2x2 matrix, right? Ultimately, correct? So this is what is called as the pandas.cross tab. Okay. So I'll be saving this pandas.cross tab in contingency table. Okay. And this is how the contingency table looks like. Okay. But yeah. And if its shape will be, of course, 2x2. The degree of freedom of contingency table is calculated using the formula number of rows minus 1 into number of columns minus 1. This is the formula. Number of rows minus 1 into number of columns minus 1. So number of rows will be data dot shape of 0 minus 1 into shape of 1 minus 1. 2 minus 1 into 2 minus 1, which is the 1 only, right? Alpha is assumed to be 0.05. Great. Next step, we extract only the arrays, right? The matrix, the array of numbers from it, because this is a data frame. It contains the index name and the column name. So you don't want that. We only need to extract the observed frequencies. This is called as the observed frequencies, right? Okay. And we can simply do contingency dot values, right? So if I do contingency table dot values, it will give me the array from this particular data frame. Clear? Okay. Once we have that in place, okay, next we feed in these observed frequencies inside the function which is called as chi2 underscore contingency. So the to calculate the chi-square statistic, okay, and the p-value, we have a function in Python which is called as chi2 underscore contingency, which is imported from scipy.stats. And that particular function takes in the observed frequencies only. So we extract the frequencies and metrics and fit it inside instead of the entire table, right? Okay. And by the way, unlike the other hypothesis tests which we have done for Z and T, which only gave us chi-square and p-value, chi-square contingency also gives you degree of freedom and expected values as well. Okay, it will directly give you the degree of freedom and expected values as well. Okay. So once we get that value, we can find out, we can see that the chi-square statistic is 0.14 and the p-value is 0.7. So which means that my alpha is 0.05. So p is greater than alpha. So it is lying in the acceptance region, which means that my null hypothesis is accepted. there is no relationship between the two columns, right? Look at this. My alpha is 0.05. My P is 0.7. It's pretty big, 50% of the entire graph. More than 50% of the entire graph in the table, right? So you can see here, null hypothesis will be accepted. Or we can also calculate the critical value. Now, how do we calculate the critical value? Critical value is calculated using similarly, just like we had critical value for T and Z. Here also we have chi2 dot ppf, right? It requires two things, 1 minus alpha value, and the degree of freedom. Very simple. All right, so let's see. So the critical value is 3.8, which is way bigger than what we had for chi-square statistic, right? So which means that either way, you go from the p-value perspective, or you go from the chi-square chi-square value perspective. Both of them will say it has failed to reject the null hypothesis, which means that it has accepted the null hypothesis. Degree of freedom is 1. Clear? Okay. In fact, here the degree of freedom which we had calculated is not even required, because it is directly giving you the degree of freedom from here, right? Correct. So we don't even need to do that, right? It's pretty cool. So we can in fact remove this out as well. We don't need this. Correct? Because the degree of freedom will be calculated from the function itself. Okay. All right. So let us look at the next question. Now, the next question says the following is the income data of blue collar workers who are at the same skill level. There are two groups of workers of the textile company, Lorries and Co., and workers of the general population. We want to check whether the variance in the income of Lorries is higher than that of the general population. I think we have already covered this question in the slide. Mean variance of general population is given as 116.11. For this is a one sample test, of course. Lorries, the sample data points are given. So if you remember, test of variance, what was the formula? If you remember, test of variance statistic formula was n-1 into sample variance divided by population variance. Now, unfortunately, in Python, we do not have an inbuilt function for test of variance, chi-square test of variance. So here, the chi-square statistics you have to calculate. Okay, there is no other way, right? So, but let's first define the alternate and the null hypothesis. The null hypothesis is very simple, same as the population. So the question is asking, you want to check whether variance in income of Lorries is higher than what is being asked to you will form the alternate hypothesis. So in the alternate hypothesis, we'll say Lorries greater than population. So please be very careful, okay, regarding this, because please not put not equal to here, because what is being asked in the question will form the alternate hypothesis. You can make it as L because it's Lorries, right? Okay. All right. So once you have that, now, okay. Now chi-square, sigma square population is given as 16.11. This is the population. Sigma is population standard deviation. Sigma square is population variance. X is already given in the question. So my length of X can be easily calculated. Alpha is 0.05. So if I want to calculate the chi-square statistic, let's first calculate the chi-square statistics first. Okay. Okay. So now Python doesn't have an inbuilt function of chi-square test of variance, right? So I have to create a function. I've created a function, very simple. So very simple. First of all, I need the formula n-1. What was the formula again? n-1 into s squared by sigma squared. This is what I have defined here. This is population variance. This is sample variance, or I can simply use the input array X and a population variance to calculate the chi-square variance, because n I can calculate from the length of X directly, right? Okay, so we don't need to bother about that. In fact, we can actually remove it from here. We don't need this, right? Now, what I need you to understand is that just like the other statistic calculations, right? It requires x1, x2 for paired t-test or no, or two sample t-test, and then it requires probably a population standard deviation or population mean, whatever it is, sample mean. So the same way I have used these two things, because the entire formula is dependent on two things: the x, right? Because this sample standard deviation will be calculated from the sample x, right? N can be calculated from the sample itself, length of x, right? And this is what has to be given to us. Otherwise, we won't be able to figure it out, right? So very simple. These two are the only parameters which it is dependent on, right? Now, once I calculate the chi-stat, I can easily calculate the critical value based on the alpha value, sorry, and then I can compare it. But I wanted to go one step further. Can I calculate now the p value once my chi-square statistics is calculated? This is something which we have not done before, because in earlier functions, the statistic value and the p value was directly given to us, right, from using one single formula. In even the previous question which we had done, right, chi-squares of independence. But now I had to calculate this manually, like putting a function there, right? Because it doesn't have an inbuilt function. By the way, you can use this function in other case studies as well. You can import this and save it in a file, import it just like libraries, custom libraries, or we can copy paste the function and run it there itself. Right? So in this case, chi-square stat is something which we had to calculate using a formula, right? Which means the p-value I have to calculate again based on the chi-square statistic, right? Because the p-value itself goes hand in hand with the statistic value. Either we can calculate the p-value from statistic, or we can calculate the statistic value from the p-value, whatever it is. So here I've calculated the statistic value, which means that I can calculate the p-value from this. How will I calculate this? Just like we did for the previous probability distributions, right? Correct? Chi2 dot PDF or CDF. In this case, it will be CDF because it's a continuous distribution. Chi-square is a continuous distribution, so we have to calculate CDF. In binom.pdf, poison.pmf, it was binom.pmf, poison.pmf. Then I think it was for standard normal distribution, it was norm.cdf. Here also the same thing. So basically, you want this area, but as I mentioned, in all these functions, distribution functions, when you have to calculate the probability between any two limits, always the values less than that particular value is always given. So in my tables, or in fact in Python, these values are recorded. So what I have to do? I have to calculate this like this: 1 minus, because I'll be calculating this probability, and out of 1, the entire probability, total probability, if I subtract this area, I'll get this value. So p value would be 1 minus chi2 CTF of the chi-square statistic, which is given to us. By the way, it requires one more parameter. When you talk about chi2 CDF, it requires one more parameter, which is called as degree of freedom, which is already calculated from above. Right? Okay. Right. So here actually degree of freedom I have to calculate again. I can simply make it as here n minus. Instead of doing this, why don't I calculate it, right? N is equal to length of x, DOF is equal to n minus 1, right? So I can make this more simple, DOF, degree of freedom. And this is DOF. Cool. Okay. So this is how we can calculate the p-value. I'm rounding out to 4 decimal places, sorry. So you can understand that not only you can calculate the chi-square statistic, you can calculate the p-value also from that. So we understood both ways, okay? If my alpha value is given, which we typically tend to assume, we can calculate the critical value from the alpha value, okay? And if my statistic value I know, I can calculate the p-value from the statistic value also. So both ways we can calculate the probability and the statistic value. Okay. So once we have this, I can call this function now. Okay. Very simple. Sigma square is the variable which I've used in this script. This is just the argument which I'm specifying for this particular function. Okay. So my chi-square stat is 35, whereas my critical value. So now p-value is of course less than 0.05. So here null hypothesis will be rejected, which means that Lori and Co has significant higher income than the population, right? There is a more discrepancy in the income than the population. But let me also calculate the critical value. Critical value kaise nikaloge? Very simple. Try to the PPF, same thing, 1 minus alpha, and degree of freedom is already n minus 1. Instead of saying n minus 1, I'll simply put it as length of x minus 1, something like this. Okay. All right. So once I have this, or you can return the do of f also, right? Return do of also. So it makes things very simple actually, right? If I return a DOF, correct, I can use this DOF here itself, right? So makes things easier. So you can see the critical value is less than the actual statistic value, observed statistic value. So from either way, from both the chi-square perspective and the p-value perspective, in this case, my variance in income of low-risk is higher than the population. And I forgot to change the hypothesis variables here actually. So once I change the variables again, I'll get the required hypothesis conclusions, right? Okay. So variance in income of low-risk is actually higher than the population. The variance in income of low-risk is more than the population. Okay. So there is one more question from the slide which I wanted to pick up, which was about the die. A die is shown 132 times with the following results. Okay. 132 times the number of trials. Is the die unbiased? If it asks, the first question which should pop up is the difficult question is always in the difficult statement should always form the alternate hypothesis. Die is biased should be the alternate hypothesis. Die is unbiased should be the null hypothesis. Now these are my observed frequencies. Now this is a different kind of chi-square test which we have to follow, right? Earlier we did the chi-square test of independence, then we did our own formula of chi-square test of variance. Here this is neither chi-square test of variance, neither chi-square test of independence. Okay, so here is a different formula, and luckily we have an inbuilt formula for this, okay, which is based on calculation of expected frequencies and observed frequencies. So observed frequencies kaise nikaloge aap? It's already given. The observed frequency is already given. 15, 20, 25, 14, 29, 28. So out of 132 times, 1 occurs 15 times. This is my observed frequency, actual. But my expected frequency would be how much? My expected frequency is very simple, right? Each of these numbers will have a probability of occurrence of 1/6 when I throw one time. If I throw 132 times, it will be simply multiplied by this probability, which will give me 22. So 22 should be the number of expected frequency, or the should be the, so 22 should be the expected frequency for each of these numbers or outcomes, right? Correct. So if this is my observed frequency, expected frequency should be 22, 22, 22, 22, and 22. 6 times, because we have 6 number of total outcomes. So number of trials, I'm recording the F observations first, the observed frequencies. Number of trials 132, but n is 6 here because we have 6 different outcomes. And if I want to find out the expected frequency, as I showed you the calculation, the probability is always 1/6, right? For one trial, right? P is 1/6. So this will be P into probability into n underscore trials. Of course, 1/6 into 132. Correct. I'll put it in a list and multiply it by that mean number of times of elements I have, which is n. So this is actually wrong. Let me run it again. Correct. 22, 22, 22, 22, and 22. Right. So I can call this probability because p value. Sometimes we write p value as p. So let me call this probability. Okay. All right. So now we have a function called stats.chi-square, not chi2 underscore contingency, not chi2 underscore PPF, chi-square. If you directly have chi-square, this function takes in 2 values. One is the F observed frequencies and the expected frequencies, right? So That is how we calculate it. Once you feed in this value, okay, that's it. Correct? Expected frequencies and observed frequencies. Let me check the default argument for this stats.chi square f underscore obs f underscore expected. Okay, so we can call test frequency with not to confuse yourself. Frequency underscore expected, frequency observed. So basically you can put it as f observed is equal to f underscore like this, and this will be this. Because this is the default argument inside the function, right? Even if you name it same way, it's not a problem. Okay, it's not a problem at all. Correct? Or the default arguments are like this, so you can simply put it like this: frequency observed and frequency expected. Okay, so this is how it goes. So once you feed in, you can see here the p-value is slightly greater than the alpha value, which is typically 0.05, right? Alpha also you have to specify here, right? So which means that my dia is unbiased because my null hypothesis will be accepted. Fail to reject the null hypothesis, right? Okay. Whereas if I want to calculate the chi-square critical, right? I can do chi2 dot ppf 1 minus alpha. This is degree of freedom will be n minus 1. So this is the n which you have. Please be very careful. Okay, it is not 132. This is number of trials, number of outcomes. Possible outcomes is n. So this is n minus 1. So, and this is not even a number of possible outcomes. This is a number of actual outcomes. Actually, it's number of actual outcomes, right? Because this is the number of outcomes which we had. So I'll write it down as number of actual outcomes from table. Okay. Observed table. So 11. So 11 is, I think, greater than 9.59, right? So again, from the chi-square perspective also, dia is unbiased. Right. Okay. So whether we go from the p-value perspective or comparing the statistical values, we get the same conclusion, of course. So we understood here in today's video that there are three kinds of tests which we have done, right? One is test of independence. For independence, we use the chi2 underscore contingency function. It requires a contingency table, right? It gives in 4 things: chi-square statistic, the p-value, degree of freedom. It gives also the expected frequencies. Whereas for test of variance, we do not have any formula. So we have to create the formula, right? Okay. And then we also calculate the p-value from the chi-square statistic using the ppf function. Very simple. Correct. And the third type was different. Third type was this, where we had the observed frequencies and the expected frequencies, and we had to check whether dia is biased or unbiased. So in that case, we use simply the function chi-square. And it requires the expected frequency and the observed frequency to be put in separately inside the arguments, right? So we have to understand that what is the problem statement at hand. Based on the problem statement at hand, we'll choose the function to be used for hypothesis testing in chi-square test. Typically, when we try to see the impact of 2 categorical variables, we directly use the first function which I used, chi2 underscore contingency, which I'll show you in the upcoming case studies in the upcoming videos. So guys, please keep on practicing, because try tweaking these alpha parameters and check how my chi-square critical value is changing, how the critical value changes when the alpha value changes, right? How does my chi-square statistic change if I change the p-value, or how does my p-value change when the chi-square statistic value changes? How are they related to each other, right? What are the null hypothesis and the alternate hypothesis which I've selected in each of these problem statements? By this time, we have practiced enough of examples. Now it should be clear how to choose the alternate and the null hypothesis, right? Okay. Please practicing, guys. I hope you're learning a lot. And This is how you actually do things in the corporate, how you do testing in the corporate. So you can now realize that whatever you do, manually is not possible when it comes to the real world. We have enough of data points, and it cannot be done manually. So we need some kind of a programming language which makes things faster. With Excel also you can do all these things, but this is much more in an automated fashion. We can actually create a function, complete function, which will do everything. Like it will check, it will calculate the test value, it will calculate the critical value, it will calculate the p value, it will assume the alpha value and compare and give you the output directly. Right? We can have three separate functions based on these three different separate uses: test for independence, test for variance, test for test for biasness, or whatever it is, right? Based on frequencies. So we can see that there are so many options available for us in Python. Correct. So this particular function is actually that function which we had used, right? Okay. E minus expected minus whole square divided by E, something like that, right? Which we had calculated for chi square, same function. But we don't need to remember the function once we don't remember the equation. So we don't need to remember the equation if we have the function available with us. So that's it, guys, for today's video. And stay tuned. Please keep practicing, keep watching the videos. It may be that watching it one time, you may not be able to get everything. So watch it a second time, a third time, a fourth time. Every time you watch a video repeatedly, you'll extract new information, guys. And please keep on practicing. See you in the next video.